Okay, welcome to day 2 of review. Today we're going to be reviewing things like factoring, completing the square, quadratic formula, and curve sketching. Should be a pretty easy one, and I'm not going to do every example. For example, the first one I'm not going to do. This is just GCF factoring, so I'm pretty sure we all know how to do that. And this next one is double bubble, so I'm pretty sure that's not going to need to happen. And the third one is dots. So again, not going to do those. But I am going to do this example of dots. It looks a little bit more complicated. Notice everything is a perfect square, which is beneficial to us because then I can just split it up to be 4z to the 5th, 4z to the 5th. That's how I would break apart 16z10. And then 25x to the 16th, y to the 14th, one of them gets a positive, one of them is a negative, because remember they're conjugate pairs. So 5x to the 8th, y to the 7th, and 5x to the 8th, y to the 7th. This middle one, because of that coefficient in front of the x squared, if you ever see that, the method that we have taught you this year is something called the triangle method. Some people call it the AC method. Basically, you take the first and the last number, multiply them together, and figure out what factors multiply to 48 but add to 19. So the winner is going to be 16 times 3. So when I pick that 16 and 3, that gives me the 19 in the middle. I rewrite the middle term in terms of the two factors that I just chose. Group the first two, group the second two. Take out your GCF for each term, and then you're not done until your bubbles are touching. So one of my factors is 4x minus 3, and one of my factors is x minus 4. The order of those two things doesn't matter as long as the x minus 4 and the 4x minus 3 are the things that are grouped together. We can factor this third example in a very similar way to double bubble. The only thing that's different is instead of putting an x in the first term, you would put an x squared as the first term in each factor. But same idea, multiplies to the end, adds to the middle term. So I'm going to pick 9 times 3. The 9 gets the negative, the 3 gets the positive. And then just kind of ask yourself if it can factor one more time. And hopefully we all agree that x squared minus 9 is difference of two squares again. So that could factor one more time. Our last two factoring examples here are what we call SOAP. Now remember, SOAP stands for same sign, opposite sign, always positive. So when we use SOAP, that stands for the fact that it's a binomial times a trinomial, so same sign, opposite sign, always positive. And then we kind of consider this to be something cubed, so we could write this as x cubed plus 3 cubed. So that becomes our a and our b. So the setup is a, b, a squared, a times b, and then b squared. So if a is x and b is 3, then a squared is x squared. A times b is x times 3 times x, and then b squared would be 9. So we can do the same kind of idea here. 4x to the third power, that'll be our a, and then 5 to the third power, that will be our b. So when I do my binomial times my trinomial, same sign, opposite sign, always positive. A, b, a squared would be 16x squared, b squared will be a 25, and then a times b will be a 20x. So if that was too fast, feel free to pause and go back, but I'm going to keep moving on because you have the capability to pause this video at any time. All right, solving for the following equations. This is literally just getting equal to 0 and factor t-charting. I am not going to take the time to go over that. I hope by now we all know how to do that. Completing the square, the first example would be very straightforward and very easy, so I'd rather do a more complicated one, so I'm going to do the second example. The reason why I consider this a more complicated example is the fact that it has a coefficient in front of the x squared. So my first step is going to be to move the 9 to the other side. And when I do that, from the 2x squared and the 12x, I'm going to take out a numerical GCF, so just the 2. So that I'm left with an x squared plus 6x plus something is equal to negative 9 plus something. I use a box. Some teachers use a space. Some teachers just use a line. It all is the same thing. Now to fill that box, I take the middle number, so in this case 6, divided by 2, and I square it. So I'm going to be putting a 9 in this box. However, because of this coefficient 2, I'm technically going to be putting an 18 on the other side. So an 18 is going to go in the other box. Now what I can do is I can double bubble this side, so x plus 3. They should be the same, always. Okay, and negative 9 plus 8 is positive 9. And I can write this as a binomial squared. Now the directions for this example say solve. If it said put in vertex form, we would be like one step away. But the fact that this says solve means I have a little bit, actually a lot of it, more work to do. So the next thing I might do is divide everything by 2. So I'm going to move over in the space over here. X plus 3 squared is equal to 9 halves. When I square root both sides, don't forget that this exponent of a 2 tells me that I should get 2 answers. Positive and negative, radical 9 over radical 2. Now we know what radical 9 is. That's regular 3. So really I have this. But I can't leave an answer with a radical in the denominator, so we need to take a second and rationalize this by multiplying the top and bottom by radical 2. So I have x plus 3 is equal to positive or negative 3 radical 2 over regular 2, and then here's my last step, is just move that 3 over. And that would be solved for x. We can use completing the square to put it in circle radius form or center radius form. Like I said, vertex form for parabola. We learned ellipses and hyperbolas this year. It would be kind of the same idea. So again, you want a binomial squared plus a binomial squared, and then whatever it's equal to, whatever your constant is, would be your radius. So, sorry, my thing's moving all over the place. Okay, here we go. X squared plus 4x plus something plus y squared minus 12y plus something, and then you always move the constant to the other side, so this would be 41 plus something plus something. So if you want to, color code or something like that, this would be my green one. This would be my blue, sparkly purple one. Oh, it changes colors. How fun is that? All right. Learning stuff as I go here. All right, to fill in the green box, I take the middle number that one corresponds with, so 4 divided by 2 squared would be another 4, so I'm going to put a 4 in both my green boxes. And then to fill in the sparkly purple one, I take the middle number, so again 12, cut it in half, square it, so 36 is going to go on both sides. And I'm going to skip a little step here. I think it's pretty obvious that this factored right here is going to be x plus 2 and times x plus 2, so x plus 2 squared. And if I factor the y one now, that one's going to be y minus 6 squared. And 41 plus 4 plus 36 is equal to 81. So you could tell me if needed the center, which would be negative 2 comma 6, and the radius if needed, and that would be a 9. All right, quadratic formula. Quadratic formula is something that is on your reference sheet. It is not something that you need to have memorized, even though most of you probably do. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So for us to be able to use this formula, we need it to be in standard form equal to 0, and then we can easily find our ABC. So when we plug all this in, negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so once I have everything plugged in, probably the next step that I usually do here is I play the discriminant in my calculator. That's just the part underneath the radical. I don't put the radical in my calculator with it. So I just type, and let's see if I can bring up my fancy calculator here. Not that I need to show it, I just want to kind of use my calculator because I downloaded it. 16 minus 4 times 2 times negative 1, hit enter. That is what I would call my discriminant, so I'm going to type that in under there. And then depending on what the directions would say, it could say simplest radical form, it could say nearest tenth. So I'm going to assume simplest radical form for this example. So if I do that, I need to reduce that 24. I need to simplify the, oops, now it was supposed to be a highlighter. Oh, well. Doesn't want to work. Okay, cool. So when I split this up, it's going to be radical 4, radical 6. And the square root of 4 is 2. Now, I tell my kids to check their triangle. So what I mean by is this number, hopefully it's yellow, yes, this number and this number divisible by the same value. And yes, all three of those things are divisible by 2, so I'm going to reduce them all by 2. I divide everything by 2. That would be simplest radical form. All right, even odd functions. So this is something that a lot of us had discrepancies throughout the year because we think even or odd degree, but that is not always the case. If it's an even function, that's when we evaluate the function at negative x, and if we get the original function back, we consider it even. If we evaluate the function at negative x and we get the negation of the original back, we consider it odd. And then if it's some kind of like mixed bag of those two things, then we say neither. We also can talk about symmetries, and we'll do that when we get to the letters at the bottom. All right, so to determine if something's even, what you would do is you would evaluate the function at negative x. So I'd plug in a negative x for every place I see an x. And I apply the exponents. So in this first spot, negative x to the 6th power, that's 6 negatives, which makes it actually go back to a positive. Same thing with the middle one, negative x to the 4th power actually forces it back to be positive, and then same thing with this one, it will force it back to be a positive x squared that's being subtracted. I got the original function back, so therefore it's even. In the next one, if I plug in a negative x and I raise it to the 5th power and a negative x to the 3rd power and a negative x, what happens is I get a negative x to the 5th, a minus x to the 3rd, and a plus x. If you notice, all of those signs have changed from the original function. Therefore, it's the negation of the original, and that would make it odd. But interesting things happen on these next two examples, because if I plug in a negative x, what I find is the first one switches, the second one doesn't, the third one switches, and the fourth one doesn't. That is a mixed bag. It's like some of them are the negation and some of them are the original. That's neither. Sorry about my handwriting, but at least you hear me saying the word. All right, so that's neither. And then this last one, this is probably the most interesting one of all of them, and the hardest to see. So the numerator becomes a negative x. The denominator stays a 1 minus x squared. This is technically the negation of the original problem and therefore makes it odd. And my best example to prove this to you is if I gave you a fraction, like this example is, and I said make it negative, you would just put a negative in the numerator, or at least most people would. Some people might put it right in front of the 1/2, but either way, you would only put one negative on a fraction to make it negative. So therefore, this would be the negation of. And odd. All right, as far as graphically goes, it has to be symmetrical over the y-axis to be even. And it has to be symmetrical through the origin to be odd. So this one's neither. This one's through the origin, so this one's odd. And this one would be neither. All right, a couple more left. Modeling. An open top box is constructed from a square piece of sheet metal. So this is my square. Removing squares of 6 inches from each of the corners. So if I remove 6 inches from each of the corners, what I find is the side now that used to be x is now x minus 12 because I cut 6 away from each corner. That means this piece right here is also x minus 12. So if I make this a 3-dimensional shape, okay, my dimensions are x minus 12 with a height of 6. It is talking about 294 cubic inches, which happens to be volume. And volume of a rectangular prism is length times width times height. If the volume is 294, the length is x minus 12, the width is x minus 12, and the height is 6, I can write this as 294, 6, x minus 12 squared. Okay, because there's two of them. And it wants me to solve for the dimensions of the sheet metal, which would be x. So actually, this problem really isn't that complicated. You just divide both sides by 6. I get 49. I'm going to square root both sides. So I get plus or minus 7, which is important, because now it's going to set up two cases. One of my cases is positive 7 plus 12, so one of my answers is 19. My other one is negative 7 plus 12. Now I have to think about this. Which answer makes the most sense? Well, obviously, if I am subtracting 12 from my original picture, so my original dimension is x, and I'm subtracting 12 from it, I can't subtract, I'm sorry, positive 5. But I can't subtract 12 from 5. That would give me a negative result. The only one that's long enough is 19. Number 2, the area of a rectangle has a corner on the reflected parabola of 36 minus x squared. So we basically have an inscribed rectangle underneath this curve. And the way that I set this up is this is an x distance and this is a y distance. And so area of a rectangle is length times width. So area of a rectangle is x times y. And since they're giving me an expression for y, I'm going to type that in my calculator. So let me bring up my calculator, if I can find it. All right, in my calculator, I'm going to go to my y equals screen. I'm going to type, if it'll turn on, y equals. All right, x parentheses 36 minus x squared. And then I am going to use my table values to help me determine a window, and it looks like in my window right here 0 to 6 and would be perfect for my x value. So go to your window and go from 0 to 6, and my y's should go from 0 to 100. Let's hit graph. I'm going to see this beautiful, it looks like a nice little mountaintop, and it wants to know the largest x value. So I need to find the maximum point. So in my calculator, I am doing second trace maximum, and I'm going to find that value. So let me get my cursor back, wherever that is. There it is. So second trace, option 4, maximum. I want left bound, and then I need my right bound, and then I need somewhere in the middle, enter. Round to the nearest thousandth, so it looks like 3.464 is going to be my answer. All right, last little bit here, curve sketching. All right, so curve sketching is actually where everything kind of comes together. This is a degree 4, so I should be expecting 4 solutions. So if I factor this out to find my zeros, I get an x squared as a GCF, x squared plus 2x minus 3. X times x, 3 times 1 is 3, positive 3 minus 1, t-chart it up. And what I just found are my zeros, or my x-intercepts. However, because this came from an x squared, I would call that a multiplicity of 2, or a kiss. So when we go to graph that, we're going to have to remember that that's going to be a kiss on the graph. So my zeros are 0, 0, because remember, multiplicity of 2, negative 3, and positive 1. So on my graph, which that was a terrible straight line, but time is of the essence here. All right, so we have something happening at negative 3, 0, and 1. What is the y-intercept? Well, obviously it's going to be 0. The degree was 4. And because it's a degree 4 and a positive coefficient, I know my ends should be up and up. So as x approaches positive infinity, the y values are going to go up. And as x approaches negative infinity, my y values should go also up. So this should end upwards, this should end upwards. So I have a kiss at negative 3, a cross at negative 3, a kiss at 0, and then another cross through 1. So there just happens to be a nice little loop there. Okay, well, thanks for listening, and